Hi, here we discuss about a project, fail-safe logic design strategies within modern FPGA architecture. Here, fail-safe architectures have become essential in modern FPGA-based systems used in safety-critical and security-critical applications, such as cryptographic accelerators, automotive electronics, and industrial control systems. In these applications, even a single fault can lead to incorrect behavior, data corruption, or security breaches, so the system must reliably detect faults and transition into a known safe state instead of continuing operation. Although existing fail-safe techniques can protect against configuration memory upsets, routing faults, and fault injection attacks, they often introduce high area overhead, complex monitoring logic, and limited support for runtime recovery. Many current FPGA solutions rely on triple modular redundancy or basic duplication with comparison approaches, which either consume excessive resources or fail to detect faults occurring inside the monitoring circuitry itself. In addition, most prior studies validate their designs using abstract FPGA models or SoC-based platforms, with very limited demonstration of fully synthesizable Verilog-based dynamic partial reconfiguration on low-cost standalone FPGAs. To overcome these limitations, this work proposes a DEFCON-inspired fail-safe architecture implemented entirely in synthesizable Verilog HDL using a dynamic partial reconfiguration region on an Artix 7 FPGA. Two identical AES-128 cryptographic cores operate synchronously within the reconfigurable region, while compact self-checking monitors continuously compare internal data path registers and output interfaces. By exploiting the dual output structure of FPGA lookup tables, the proposed design achieves resource-efficient redundant XOR and OR comparison logic, ensuring that faults within the monitoring logic itself do not mask functional faults. A hierarchical alarm generation and compression network guarantees reliable fault detection under single fault and selected dual fault conditions, and a fail-safe output blocking mechanism forces all outputs to a predefined safe value when a fault is detected. The design is synthesized and implemented using Xilinx Vivado, achieving positive timing slack, low resource utilization, and modest power consumption, demonstrating a practical, reusable, and effective fail-safe framework for real-world FPGA systems. Now we can verify this paper. This paper is fully designed to predict the data mismatch from the AES operation which using DEFCON. This initial architecture from this paper presented with Figure 2, it shows the internal CLB structure created by OpenFPGA consisting of 10 6-input LUTs connected through a fan-out free local routing network. Each LUT input is driven by a configurable multiplexer, enabling flexible logic mapping while maintaining structural independence of LUT outputs, which is useful for fail-safe design. And Figure 3 illustrates the global FPGA routing architecture, where a central CLB is connected to surrounding connection blocks and switch blocks. This structure defines how signals fan out and route across the FPGA, highlighting the role of configuration memory in controlling routing paths and fault propagation. And Figure 4 presents the proposed DEFCON fail-safe circuit where redundancy and self-checking are implemented at the LUT level using a carefully programmed multiplexer-based structure. Each redundant XOR is realized inside a single 6-input LUT by exploiting its dual-output multiplexer network, which naturally forms two independent logic cones. The LUT configuration memory is programmed so that each cone depends on a different replicated pair of signals, ensuring that a fault on one input or within one logic cone cannot affect the other. This allows a single LUT to act as a fully self-checking comparator, capable of detecting both functional unit mismatches and configuration memory faults. The outputs of multiple R XOR units are hierarchically combined using non-redundant and redundant OR gates, forming an alarm compression network that guarantees at least one alarm assertion under fault conditions. The multiplexer network operation provides strong fault isolation, minimizes reconvergent paths, and enables compact realization of redundancy with low area overhead. The main advantages of this approach are improved fault coverage, detection of faults inside the monitoring logic itself, and significant reduction in LUT usage compared to conventional duplication or triple modular redundancy schemes. And the final architecture presented in this paper integrates a DEFCON-based fail-safe monitoring system within a dynamic partial reconfiguration framework on a Xilinx Zinc 010 FPGA. The design is partitioned into a static region and a DPR region. The static region contains the ARM Cortex-A9 processor, GPIO interfaces, and the PCAP configuration logic, which together manage control, data transfer, alarm observation, and fault injection. The DPR region hosts two fully independent and synchronously operated AES-128 encryption cores, ensuring identical inputs, keys, and control signals to enable reliable duplication with comparison. Two DEFCON monitors are placed alongside the AES cores inside the DPR region. DEFCON 1 continuously compares the 128-bit internal ciphertext round registers updated at every encryption round, while DEFCON 2 monitors the 32-bit output readout bus. The outputs of the DEFCON monitors are hierarchically compressed into multiple alarm signals, which are registered to capture transient faults. When any alarm is asserted, a dedicated blocking module forces the encrypted output bus to a predefined safe value, preventing faulty or corrupted data from leaving the DPR region. At the top-level module, the design instantiates the DPR wrapper, two AES cores, two DEFCON monitor modules, and the output blocking logic, with clearly separated control and data paths for redundancy. The top module interfaces with the static region through GPIO-based control, data, and alarm signals, while partial reconfiguration is handled via the PCAP interface without disturbing static logic. This modular top-level organization ensures fault containment within the DPR region, supports runtime recovery through reconfiguration, and provides a scalable template for implementing fail-safe cryptographic systems on FPGA platforms.
And this work we designed in Verilog HDL, functional verification done with ModelSim, synthesized in Xilinx Vivado Arctic 7 FPGA. Now we can verify the coding top module architecture. Now we can verify the simulation results. This is normal simulation output. Here, the all alarum will 0 only. If we create a manual error, it will indicate the alarum. Wait, we will show that. This is the error-based simulation output. Once the AES data mismatch, the alarum will indicate the signal with support of DEFCON mechanism. And this code we have synthesized in Vivado. This is the results. This is an RTL schematic. And this is a comparison document. And we written an abstract document for this work. Title, base paper abstract, objective of this work, proposed title and proposed abstract, related notes. Finally, literature survey and references. Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.